Okay, so a little bit about me. I'm actually a computational chemist. I work at Berkeley Lab. I have a group there that does actually high-performance computing, quantum computing, and machine learning. So all the buzzwords you can think of nowadays in science. So today I'm talking about a little bit of the work that has been done by three of my postdocs. Yu-Hang Tang and Tess Smith are both Alvarez postdocs, so they pretty much do whatever they want to do in their own research. And the other postdoc is Muammar Al-Khatib, who recently started in my group. So what we're after is, as I said, I'm a computational chemist, and so we're interested in really figuring out how we can learn about the chemistry using machine learning models. So if you look at literature in chemistry right now, there's a lot of work that has been done where you take 3D structures, coordinates, and you are able to predict certain properties, especially things like energies, total energies. These are relatively easy properties to do because they have electron densities which are continuous. So changing coordinates, the electron densities adjust. So they're relatively easy to do. So that is relatively doable nowadays. There's a lot of work that people are doing for that. But we're really interested in the other way around. Can we actually take a desired property and find a structure, which means a material structure, a molecular structure? Can we actually do some rational design or have the machine learning network do some rational design? So we've been working a lot on trying to figure out what the right way is to use generative models in the last year or so. So we have mainly focused on autoencoders, as you heard, and the other thing we have been working on is marginalized graph kernels. So what is the challenge for us when it comes to using generative models? So we really always are wondering how we can encode molecules and in a way that we can generate realistic ones. So if we go into a latent space and we choose any point in that space, do we get back a molecular structure that is realistic? Of course, there's a challenge there. Molecular structures are by nature discrete. So a continuous representation of something that by nature is discrete is an interesting challenge. So as I said, we've been trying some different generative approaches. The other challenge that we actually have is, can we build data sets that are large enough, and what is large enough? How much data do we really need? And then if we can take all those pieces, put them together into a machine learning network, can we really generate molecules with the desired properties? So we haven't gotten to the last point yet, but we're making strides towards it. So the question, of course, in the long run is, how do we reliably encode 3D structures? The key part is we need to have something that is very information rich. Effectively, we need to try and figure out how to encode some of the physics that is described by 3D structures. 3D data in general is still a tricky thing when it comes to deep learning. As I said, we need physical constraints, and again, we need to effectively encode this in a continuous space where we know we need discrete structures. Two atoms are never going to sit on top of each other, for example. We also know that molecules or materials have hierarchical structures. So that's another feature that we are trying to exploit. So there's many different ways of encoding atomic structures. They're good for certain functions. They are not good for other functions. There's a real, I'm not going to go into details here. There's a large number of people that work mainly from coordinates and smiles, although there is a lot of literature, a long-standing literature dealing with graphs. Some work that is done by another person in my group, Sylvia Corvelli, is actually where they used images, just simple 3D images, volumetric renderings of 3D images, to actually encode the molecular structure. So if you're no physicists or chemists, I'm considering myself more a physicist than a chemist sometimes, but there is always a desire to find all the symmetry that we have, simply because we simplify our problems. If we have a threefold rotational symmetry and we know what the symmetry is, we only need one of the three atoms, for example. The rest we can generate. So you have similar things in general in materials. if you look up the left, you have effectively two octahedrons that have a slightly different orientation. They're the same octahedron, just rotated. How can we actually encode that kind of symmetry, that kind of rotation in a neural network? And for us, it's also very easy to do rotations that change a structure, for example, octahedral, to a trigonal prism. So how do you encode those kind of rotations and transformations? So the solution, this is work that was done by Tess Smith, and some of you might have already heard about that before, is use tensor field networks where they use convolutional filters based on spherical harmonics. And if you go to L equals 0, you have just no symmetry to deal with at that point. The higher you go on the L, the more opportunities you have to encode certain symmetry properties in the molecular system. So this all becomes then a geometric tensor, and it's all tensor algebra. So there's a paper on arXiv on this that she has published. Well, not published, it's on the arXiv. But to show you that tensor field network actually can do some interesting things is, let's assume that you have that molecular structure on the left, and I take that atom away that's in that circle. Can the neural network actually generate that extra atom back? And surprisingly, if you look at a table, this neural network based on tensor fields can actually recover the missing atom at about 90% accuracy. And this is for a relatively small set of molecules and training a small set of information. So that means that these kind of techniques actually do help you. And the paper has some other examples of how you can actually use symmetry to do some of these kind of things. So some of the things that we've done, and as exploring the generative models, we've done the GANs that you've heard about already. Our biggest challenge with GANs is to find a very good way to design a loss function. So how do you know if something is bad? And once you start to do that, you effectively realize that you pretty much have to encode all the physics, and that defeats the purpose. So the two that we have been focusing on a lot more is variational autoencoders and marginalized graph kernels, and I'll show a few slides on that. And again, I want to stress on the bottom is that, so when we talk about chemistry or materials, what we're generally measuring is electron densities, which are smooth, relatively smooth functions over space. What we are often encoding are atoms, and those are coordinates that are localized, and they are discrete. So there is an interesting challenge there, is that some of the properties that we're trying to get to are continuous, but we have to encode our information often in a discrete way. So the interesting part of autoencoders is, of course, our goal is to see if we can find an atomic map and actually start to think about what is the relationship between a silicon crystal and a benzene molecule. Would be an interesting challenge. Now that's extreme, but if you start to think about proteins, for example, that have similar functionalities, you should be able to start to relate the key features of those proteins to the function that they are performing. So the autoencoders that were nicely explained in the last talk too. So the autoencoders allows you to do two things. Once you have a latent space trained, you can add new layers and do specific tasks that any deep learning network can do right now, which is predicting energy and forces. But what we're after is really being able to use this as a generator and actually start to decode the layers and try to see if we can find new hypothetical structures that are realistic. The other approach that we have been working on, so this is work that Yuhang Tang has been working on. The paper that came out very recently is in JChem-Phys, where he actually is using regression combined with marginalized graph kernels. Now it's a very busy picture, but effectively what he does, he generates a graph of a molecular structure using some adjacency rules, and then combines those two graphs in a way that allows them to really do kind of a similarity mapping of the two molecules, as you can see here. There's a clear pattern here of these molecules where we just have an extra carbon oxygen at the end. We can see the difference and the similarity between those two molecules. So this approach actually he has been testing for a pretty small set, which is about 8,000 molecules. But there's bigger ones called QM9, QM10, QM11, which just grows the number of molecules. But so he tried to do some of the training for this in different ways, using supervised learning and unsupervised active learning. And I want to point a little bit to the unsupervised active learning. What he really realized is that we have a lot of structures that are similar. So we don't have to learn with the same structure over and over again. He can actually use the similarity, and he can actually use the regression kernel to get a confidence that he has seen this structure before. And by knowing that he has seen this structure before and only training on structures that he hasn't seen before, he can actually train a lot quicker with a lot smaller sample size. But he can actually get very accurate results. As you can see, this is in the order of less than a kcal per mole, which is what's considered chemical accuracy in a very small training set for a molecule that is not that small to do. This actually, the data that the accuracy that he has actually beats all the other ones that are out there in the literature. So last point that I want to bring up is this is the work of Muammar. He's working with me to actually generate a lot of data sets for more of the metabolomes, which are biomolecules that are formed in reactions in proteins. So when we started to do a lot of the data generation and also the analysis and the building of machine learning networks, we really quickly realized that, well, somebody needs to be able to reproduce this at some point. And if you're generating this network, I don't want to generate it again from a piece of paper. Just give me something that is easy to use where I can do small modifications. So when we were talking about that, he's like, I'm going to build a little framework. So it's called ML for Chem, as machine learning for chemistry, where he has built a Python framework that has a PyTorch backend. It used Dask for distributed training, and it has, for us as chemists, it uses the atomic simulation environment for support, so generating data structures, for example. It also has some visualizers and other pieces. So he's been working on this, and he's adding more functionality, such as a different type of atomic-centered models to encode your information using symmetry functions, neural network potentials, deep autoencoders. He has one loss function that he has encoded right now, but he is adding some other loss functions. So it allows you to simply take something and say, I want to use this way to encode, this way to compute. This is the model that I would like to use. And then effectively, it's a very short piece of Python code to actually run this. This will run in parallel. So he chose here a small case where he has 200 molecules, 4,000 features, and actually does the optimization of a neural network training. And I don't remember exactly which one this is, but so this is some of the work that he has been doing in generating a software infrastructure, which is on GitHub, so it should be accessible. One of the tools that he has, which allowed us to really look at some interesting features, is a visualizer for the latent space. So on the left, we have PCA. On the right, we actually have some distributed stochastic neighborhood embedding, which allows us to actually separate better the different pieces of information and actually start to look at the correlation between different atoms in these kinds of models. So, so I hope I showed you some of the work that we've been doing in the area of machine learning for chemistry. So Mostly it's chemistry, but we also do a lot of materials now. And that work really was supported both by the 2 postdocs, by the 3 postdocs, and a little bit by my time through LBL's LDRD. We also have some collaboration with Kidware right now. Those that have done chemistry then know about the Avogadro environment. We're actually building a Jupyter Notebook version of that right now that allows us to integrate actually YAML for chem and some of the data generation capabilities. So that's all that I'm going to talk about.